VLSos here. This is a video lesson on continuity. This time the presentation is going to be more formal because we're going to base our justification for discontinuities on the three rules that must exist for a function to be continuous at a point. The formal justification for continuity requires these three things: that at every point a value exists, and at that same place the limit exists, and that at that location the value is equal to the limit. So if we had a function that we wanted to prove was continuous, we would focus on features of that function that would indicate that there may be a discontinuity, and then we would go through the process of justifying whether the function was continuous or not continuous at that point. Because it is not possible to test these three rules for every single point in the domain of a function. Functions often have an infinite number of points in their domain. We go about testing for discontinuities in order to show where problems and features of a function might lie. In the second rule listed here, the limit must exist. That means that's implying that it's the absolute limit that you're talking about here. It's an independent justification that the one-sided limits must be equal to justify that the absolute limit exists. But in justifying formal continuity, you don't need to include as part of your work the justification that the absolute limit exists if you can determine that it does. We will look at the same function that was graphed for informal continuity, but we're going to be a little more rigorous with the locations of the discontinuities. We had a discontinuity in the function that looked like this, which we called a vertical asymptote or an asymptotic discontinuity. We had to lift our pencil in order to continue drawing the graph across this location that we will say is at A. We had a jump discontinuity when our function ended, and then we continued along on another piece, and we will label the jump discontinuity at B. We had to lift our pencil at a removable discontinuity in order to continue. We had a corner as a feature of the graph, which does not require lifting the pencil to draw, so there is no discontinuity at corners or cusps. And then we had another type of removable discontinuity where the function had a value somewhere else before continuing on. We'll give locations for these discontinuities C and D. Now at each discontinuity we had to lift our pencil. So informally we know that there's a discontinuity there. But formally, how would we justify it? Well, at A, each one of these we would go through our list. At A, we look for a value, and immediately we can see if we have a vertical asymptote, then that's an indication that A is not in the domain of our function. We don't have a value at A. So rule 1 is a bust already. At A, it's a discontinuity because we have no value. We could go on and we could say that we don't have a limit either. The one-sided limits from the left and the right are not equal. From the left it's in positive infinity. From coming to A from the right is negative infinity. Those are not the same, so there's also no limit. And remember, when we're justifying that it is not continuous at A, it's sufficient to say there's no limit. We don't also need to say there is no limit because the one-sided limits are not equal. That's enough, no limit. And the limit and the value can't be equal if they don't exist. Part B, or at location B, We look for a value, and it does exist. It's the closed dot, so that's good. We look for a limit. The limit does not exist. The right and left sided limits are not equal. They arrive at different values when you approach B from either side, and so we have no limit to justify that it is not continuous at B. And if there's no limit, then the value can't equal the limit. Notice that it doesn't need to be stated that the value and the limit are not equal if one of the first two rules has already been a bust. At C, it is not continuous. We know we have to lift our pencil, but why? There is no value. It's an open dot. So, no value. Now, it's worth saying that the limit does exist. We can approach this location from both sides, and we think we're going to be at the same place. So the reason why it's discontinuous is there is no value. And at D, we have a value, it's the closed dot. We have a limit as we approach this location from the left and the right. We think that we're going to the same location, so the limit exists. But the reason why there is a discontinuity at D is the value that does exist is not equal to the limit, which also exists. Now, we could be more rigorous and more formal with this if we had a function or the algebraic expression for this function, and if we did, then we would need to abandon our graph, which is just giving us a good idea of what's going on. It's a visualization. So the graph itself has some inherent inaccuracies in its presentation. If we had the expression for the function, we would need to use it to be able to state these things with the actual algebra.